Everyone, welcome back to Forward CloudSec. Before we continue, we'd first like to thank our sponsor, Skyhawk. Skyhawk Security has built the first cloud breach prevention platform, monitoring threats, correlating them into an attack storyline, offering remediation recommendations and automation, enabling our customers to take action before a full-blown breach occurs. Learn more at www.skyhawk.security. Next up, we have gVisor, the future of container security with Andy Nguyen. Thank you, Andy.
Hey, everyone. Thank you very much for having me here today. My name is Andy Nguyen, and I'm super excited to talk about gVisor from the perspective of a hacker. I'm a security engineer at Google, and I work in cloud vulnerability research team, where I focus on low-level security. We research and look for issues in various security boundaries, and gVisor is one of them. You might also know me as The Flow. I'm a console hacker who has published multiple exploits for PlayStation devices. The latest is a Blu-ray disc Java jailbreak for the PS5. So let's jump straight into the topic. What are containers? That you probably all know already about. They are packages of software that contain all of the necessary elements to run in any environment. But what are containers not? Containers are not a sandbox. There's no secure isolation boundary between the host OS and the application. Containers use lightweight OS-level virtualization, which means that they run on the same kernel, and hence, a Linux kernel vulnerability would allow them to escape to the underlying host OS. And as you all know, there are many Linux kernel bugs. To make containerization more secure, Google invented gVisor. It is an open source application kernel that implements a substantial portion of the Linux system surface, which is called the Sentry. And gVisor provides an OCI compatible run as C binary that allows you to create secure containers with the usual commands. And there are many different flavors of gVisor, and the team has been experimenting a lot to provide various secure options. We call them platforms. And a platform needs to provide three things. It needs to implement syscall interception, basic context switching, and memory mapping functionality. And we offer three solutions. First is KVM, which basically runs the container application inside the guest in user space, and the Sentry, which is the emulated Linux kernel, runs as the guest kernel. And next, we have ptrace, which uses the ptrace sysemu option to intercept syscalls. However, and here the Sentry is the parent process. And finally, our recent addition is the systrap platform, which is quite similar to the ptrace platform. However, it intercepts syscalls using seccomp. So basically, instead of performing a syscall, the kernel sends a sys signal back to user space, where a stop is installed to catch the signal and to propagate the signal information to the Sentry via shared memory. The coolest thing about systrap is that it does sophisticated binary patching in order to replace syscalls by jumps. And this allows syscaller to accelerate invocations of syscalls because the overhead of context switching is reduced. So as you can see, the ptrace and systrap platforms architecture is quite unique. Different from Firecracker or other solutions, it does not rely on the hardware virtualization, and as you probably know, nested VMs do not perform very well. How is gVisor secure? It follows 4 security principles, which I will present next. The first principle is the principle of defense in depth. Basically, no single vulnerability should compromise the host. In gVisor, you need at least 2 vulnerabilities to defeat 2 very strong security boundaries. The first is between the untrusted application and the Sentry, which is the emulated Linux kernel written in Go. And the second is between the Sentry and the host, which consists of namespaces and very strict seccomp BPF policies. Since there are many file system-based attacks, the Sentry process is also isolated from host I/O operations. Namely, there's another proxy process also written in Go, which is called the gopher, that the Sentry can talk to via Unix domain sockets. And finally, since there are many vulnerabilities in networking syscalls, gVisor offers a custom network stack. The second principle is the principle of attack surface reduction. As of today, the Linux kernel has around 350 syscalls, out of which gVisor only uses 30 to 50 syscalls, depending on the options. And not only does it limit syscalls, it also performs aggressive arguments filtering. As you probably know, syscalls such as IO control, setsocopt, getsocopt accept lots of commands and options, and there have been a lot of vulnerabilities in these. In gVisor, only commands and options that are actually used are enabled. And the third security principle is the principle of least privilege. To achieve that, all processes run with a pivoted root in a new mount namespace. And of course, like normal containers, they also run in new IPC, UTC, user and network namespaces. As mentioned before, all processes are restricted by seccomp BPPF with the least possible number of syscalls. For instance, only the gopher process that handles file operations can do file syscalls such as open@, whereas the sentry process does not have access to these syscalls. And finally, the last principle is the principle of secure by default, which is that the most secure options are chosen by default when you use the gVisor run as C binary. For instance, the custom network stack is something that is enabled by default, and if users prefer, they can choose the network pass-through option. And most importantly, and this is why Google decided to re-implement the Linux system surface, is that most of the code is written in the memory-safe language Go, which means there are no out-of-bounds accesses, buffer overflows, or uninitialized memory vulnerabilities. There are also no use after freeze or double freeze and many other bugs that exist in C and C++. Of course, there's a caveat. Misuse of the unsafe package can still lead to those issues. And unfortunately, we still need to rely a bit on unsafe pointers for certain optimizations and mainly to interact with the syscall interface, because that's what this Linux kernel expects. At Google, we do continuous reviews and research, we audit new features, and we perform vulnerability research. One thing I like is that there's a convention of placing every function that uses the unsafe pointer in explicit files called unsafe.go. And this eases the review because the reviewer knows which files to carefully audit. Of course, not only do we take gVisor manually apart, we also have automatic fuzz testing. We use gVisor for that, also by Google, to detect issues in Sentry. However, most of the issues found are locking issues or null pointer exceptions, which are not exploitable. Now, let's dive into some vulnerabilities that we found during our review and research. The first vulnerability is in the command to get the interface configuration. Namely, in the network pass-through mode, the implementation of the syscalls simply forwards the command to the host. And the gVisor team introduced a very subtle mistake, however, with some consequences. We found this issue by carefully auditing all the allowed IO control commands. The bug was the wrong structure was used instead of ifconf, ifrec was used. Sorry, the other way. Instead of ifrec, ifconf. So there's a small difference between these two structs, as defined in the Linux source code. The ifconf struct is a struct that has a length and a pointer to a ifrec struct in a union. And due to this confusion, an application can provide an arbitrary ifrec pointer and lets data to be written to it. With the following example, the data below can be written to 41414141. The content is not controllable, but this is in general not a problem. For the Linux kernel, we demonstrated that a single byte out of bounds write would already be enough to achieve kernel code execution. For instance, you can just overwrite a heap pointer and redirect to a controlled data of yours by spraying the heap. In gVisor, exploiting write-where primitives is easy, unfortunately, because if we look at the process maps, we see that the Go binary and the Go heap are located at constant addresses. This is currently a weakness of gVisor, and the team is currently working on enabling Pi. So because of this weakness, with the write primitive, an attacker could try to corrupt data in either the data segment of the binary or the Go heap. The second vulnerability is in the new systrap platform. As mentioned earlier, syscalls are intercepted with seccomp, and the signal handler is installed, which catches syscall signals and propagates this information to the sentry via shared memory. And this shared memory is called the sys message. The sentry then reads from this shared memory and emulates the syscall. So every time you hear shared memory, a bell should ring, namely, if multiple processes can read and write from the same memory, it could be prone to double fetch race conditions. On Windows, for example, this is a very common bug class. The user space can provide a buffer, and since SMAP is not enabled, the kernel does not need to copy the buffers to kernel memory first, but it can just directly access it. Now, if for instance, a size integer is read twice from a buffer, first to validate and second to use, an attacker could, for instance, first provide a small size, pass the validation, and then quickly swap to a bigger length to cause issues such as buffer overflows. So we went through all of these members of this sysmessage struct, and we tried to find instances where changing the values could have led to unexpected behaviors. We couldn't find such double fetch issues, but we found out that one of the fields was used in an interesting way. Namely, there's some code that saves and restores the floating point state of the guest application. In memory, the floating point state is located close to the sysmessage structure, and hence a relative offset was used for that. This offset is 64-bit and is fully controllable by the application. And they use it for an unsafe slice copy in both directions. As such, this is an out-of-bounds read and write vulnerability. And now we demonstrate how to trigger the out-of-bounds read and write to leak and corrupt memory. In the application, which we call the guest, we spawn a child process, which is ptraced. The traced guest child triggers a signal to the sentry, and the sentry will save the floating point state and then wake the guest parent up. The parent can then invoke ptrace, getRecset, or similar syscalls to fetch the floating point data from the guest child. And since the offset of the floating point data can be controlled, a different offset can be provided, in our case one that is out of bounds, in order to leak data. In order to achieve an out of bounds write, the guest child can also trigger a signal to the sentry, which will first save the floating point state, and then the sentry will call the signal handler, and the guest child can then modify the registers, and on sig return, the new registers will overwrite the floating point data in the restore method. Here again, we use a different offset to write controlled data out of bounds. How do we turn a relative out of bounds read and write into arbitrary read and write? Since we have a relative out of bounds read and write, we just need to find out the base address. And for that, we basically ran gVisor in GDB, and we searched for a pointer in the proximity that we could use to deduce the current position. We found that there's always an adjacent mapping to our message, which contains a pointer to the next mapping, which is perfect. With some calculations, we should be able to deduce the base address. So we used the real primitive to leak the value at the offset hex 9000, and which is a pointer to some other object at hex 40,000. And we simply subtract hex 9000 and hex 40,000 to calculate the base address of the sysmessage structure. And so with the base address of the message, we can do arbitrary read and write. As mentioned earlier, the current weakness is that the Go binary is located at a constant address. This makes exploitation especially easy. In order to achieve rip control, we can simply corrupt a function pointer in the data segment. For instance, the VDSO clock get time symbol. And this function is called periodically, and with our proof of concept, we managed to get a jump to 4141, 4141. This vulnerability was discovered during a review before launch, and it would have allowed compromising the sentry and as such elevate privileges. Now, what's the next step? with redirected control flow, the typical approach is to do a stack pivot and then perform rob chain execution. In the rob chain, one would then execute system to execute a binary, or call mmap to map a read-write executable page for the payload. But of course, the execv syscall is not available. gVisor does not allow you to execute a different binary. And as defense in depth, it is also not possible to map executable pages. This is a recommendation from our team after we found the first type confusion vulnerability. This mitigation means that the attacker is only able to do rob chain execution in the sentry process, and a lot of root causes of Linux kernel vulnerabilities are race conditions, and exploiting such bugs in pure rob may be quite tricky, though of course it's not impossible. One technique, for example, is to install a syscall proxy implemented as a rob chain in the sentry process that the application can delegate syscall invocations to. And at Google, we have a program called KCDF, where we pay big bounties for Linux exploits. We pay in a range of 100,000, and we have gotten like more than 20 submissions in the past around 2 years. We analyzed all of these submissions and checked if they affected gVisor. As you can see, none of them were able to defeat any of the layers of gVisor. The only bugs that affected gVisor were CPU ones or in the run as C itself. To recap, gVisor comes in many flavors, with the most secure options enabled by default. gVisor's architecture is quite unique, and it provides 2 strong security boundaries, making a full guest-to-host escape very difficult to achieve. And gVisor has continuous fuzzing and continuous reviews and research to ensure there are no bugs and vulnerabilities. The 2 vulnerabilities we showcased were the only ones we found that were high severity, and they were in the unsafe usages. The amount of those is very low, and we carefully audited all of the unsafe pointer usages. With that, I would like to conclude my talk. Thank you very much for your attention. You can learn more about gVisor at gvisor.dev. Again, gVisor is open source. There's lots of documentation, and they are always happy for contributions and pull requests.
Hi, thanks a lot, Andy. So some questions I had. First, you talked a little bit about, in the title of the talk, the future of container security. Like, where do you imagine gVisor going over the next year, 2 years, 5 years? Like, what would you want to do next to make this sort of an even stronger container isolation platform?
It's a very good question. So just to clarify, I'm not on this gVisor team, so I'm not contributing to the features of it. But so we are a separate security team which looks at all of these security boundaries. I can't give a good answer for this. I know that they are still researching, still making new platforms which are more performance. For example, one of the latest changes, which only compromises security a little bit, is to get rid of the gopher process because they realized it had a lot of overhead for file operations. So now they are getting rid of this, and they are providing a less secure option, which is called direct FS, where the sandbox application can just access the host file system directly.
And then how do you think about sort of the benefits versus isolation of something like gVisor compared to, you mentioned Firecracker, which uses a hypervisor to achieve isolation among the workloads. Like, what do you think about how would you compare like the trade-offs of these?
So for Firecracker, there's the KVM, which is a very strong security boundary. I think in the past there has been only one like public guest to host escape, also from Project Zero, and it was in a feature which was not even fully rolled out. Like it was like recently added, and I think no upstream kernel was affected, no LTS was affected. So gVisor also has this option to use KVM, But as mentioned before, they have various other platforms which are provided at Google, where you can sandbox your application without hardware virtualization.
And then what do you see as like the barriers to adopting gVisor, if any? Like, how do you think people should start using it more? Why isn't it more widely used?
Good question. Good. So I think it should be very easy to adapt. Like, it's open source. You can run it on any. You can run it on AWS. You can run it in GC VMs. And we also use it for our production. So I think it should be very easy to use, and I think that's one of the main focus of the team.
All right. Well, thank you very much. And then just a note to the rest of the attendees: we'll be taking a break, and we will be back here in this room at 3:20.